The fundamental theorem of line integrals has shown us that if we start with a conservative vector field, line integrals for that vector field are always path independent. Line integrals only depend on the beginning and ending point of the path and not exactly how you get from the beginning to the end. We think that if you have a vector field with independent line integrals, then hopefully the vector field is conservative. Let's actually prove that fact. So we're going to start with a vector field that has path-independent line integrals, and we want to show that f is conservative. So what we're going to do is fix a point A, and point A is going to be the same point for everything that we do from now on. And to show that f is conservative, we have to somehow come up with a potential function for f. And here's how we're going to do that. For any point x comma y, we have to define what little f of xy is. And what we're going to do is just pick any path from A to that point, and we will declare that little f of xy is the line integral over that path from little a to x comma y. So we have two questions to answer about this definition. The first question that we need to answer is this function that we've defined, little f, well defined? And the question of something is well defined is, often definitions involve some arbitrary choices, and you'd like to know that your definition doesn't depend on the arbitrary choice that you made. In this definition for little f, the arbitrary choice that we made was how you get from the point A to the point x comma y. Because there are many paths that you might take to get from A to xy. For example, you might use this curve, we'll call that C1, and you might use this curve, which we'll call C2. So if you have two different curves, we need to know, is it true that f of xy, what the definition gives us for f of xy, is the same for both curves? Because if it were different, that would mean different choices of curves would give you different outputs for the function little f. But one function can't have different outputs for a single point x comma y. So translating this question, is it true that f of xy is the same for both curves? Well, let's just translate that into the definition of little f of xy. So if you use the curve C1, then little f of xy is the line integral over C1 of capital F dot dr. And if you use the other curve, C2, to calculate little f of xy, what you get is the line integral over C2 of capital F dot dr. And we need to know, are these equal? But asking if these are equal or not, that's just asking if the line integral is path independent or not. And we assumed at the very beginning that f has line independent path integrals. So the answer here is yes, because f has path independent line integrals. All right, so that unfortunately leaves the second question that is a little harder to answer. And our second question, let me move over a little bit. Our second question is, remember we had this function, this vector field capital F, and we produced a function little f. We were on the lookout for a potential function for capital F. So now we have this little function, this function little f, And we need to know, is little f a potential function for capital F? And this is kind of a hard question to answer because we know so little about capital F and the function little f. Capital F, the only thing we know about it is that it has path-independent line integrals. And little f, the only thing we know about it is the definition of little f. And just to remind you, the definition of little f is little f of x comma y is the integral of capital F dot dr, where our curve goes from our fixed point A to the point x comma y. So we need to somehow convince ourselves that if we take the gradient of little f, is that equal to capital F? Well, just to name everything in sight, let's say that capital F is p comma q. So p and q are both functions of x and y. And to check if the gradient of f is, the gradient of little f is capital F, we need to know that partial f partial x is equal to p, and partial f partial y is equal to q. So let's focus on just one of these. Let's take the first one. So we need to, now we need to calculate somehow partial f partial x. Okay. The problem here is that we don't know very much about the function little f. So here's what we're going to do. Here's our fixed point A, and here's our point x comma y. And to calculate f of x comma y, we can choose any path from A to x comma y, and we're going to choose a very special path. So the first part of our path is going to go from A to a point very close to x comma y, and this point I'm going to call it x naught comma y, and it's so close to x comma y that all we'll need to do to get to x comma y is just move to the right a little bit. This part of the curve I'm going to call C1. The second part of the curve from A to x comma y is going to be this line segment that moves entirely horizontally. So this little line segment just goes to the right. And this line segment we're going to call C2. Okay. Now, so let's look at f of x comma y. We'll take the derivative in just a little bit. So f of x comma y is the integral over this path, C1 and C2, of f dot dr. So that's the integral over C1 of f dot dr plus the integral over C2 of f dot dr. All right. And let's parameterize the second integral. So to parameterize this integral, so to parameterize just this blue segment of C2, well, this is a straight line that goes entirely horizontally, And so the x-coordinate in this line segment is changing, so let's use just our parameter t. And the y-coordinate on this part isn't changing, it's always y. Now that we have so there's our formula for our parameterization, and the values for the parameter t, well, our x-coordinates along this blue line segment start at x naught, because that's the left-hand end of C2. And they go up to x, because that's the right-hand end of C2. So now that we have a parameterization of that part of the curve, we can calculate r prime. And we just get 1, 0. And we can use this to parameterize the second integral. The first integral, we're going to leave it unparameterized. So line integral along C1 of f dot dr plus the integral along C2, and the t values for C2 are from x naught up to x of f of r of t dotted with 1, 0 dt. So this is integral of C1 of f dot dr plus the integral from x naught to x. Now this vector, the vector field capital F, remember that's just p comma q. And when you dot, so this is just p comma q, and when you dot with 1, 0, that just selects the first coordinate. So this dot product is just p of x, p of r of t dt. All right. So integral from C1 across C1 of f dot dr plus the integral from x naught to x of p of, and on this, for this curve r of t, right, so we would put x right here, but our parametric curve tells us that x is really just t, and we would put y right here, and our parametric curve tells us that y is, well, it's just y dt. All right, and remember this is all f of x comma y. Now finally we're in a position to calculate the derivative that we were ultimately after. So partial f partial x, and this is partial x integral along C1 of f dot dr plus partial x integral along from x naught to x of p of t comma y dt. All right, now to evaluate these derivatives, this first part, well, if you look at C1, as x changes a little bit, what happens to the curve C1? Well, let's go up and look at our curve C1 way up here. Changing x a little bit moves this point, our final point, back and forth just a tiny amount. And it's a tiny amount because we're taking a derivative. So ultimately, this is all built on the limit of the change in x going to 0. So since this point is moving back and forth in the x direction just a little bit, it never interferes with the point x naught comma y. So it never passes the end point of C1. All of that means that this path C1, it isn't going to change at all as the ending point, x comma y, moves around a little bit. And that means that this line integral, nothing in this line integral changes when x changes. But if this line integral doesn't change when x changes, that means this line integral is all 0. All right. Now, what about this second line integral? Well, if you look at this second line integral, we have a function of one variable. P is a function only of t. Y is a constant here. Remember, along this part of the path, y is constant. So the only thing that changes in this integral is t. So we have a function of a single variable, and we're integrating from x0 to x. And we're letting x change a little bit. We're taking a derivative with respect to x. Well, this is exactly the situation that the fundamental theorem of calculus applies to, where we have a function, we're integrating from a constant value to the variable, and then we're differentiating with respect to that variable. So the fundamental theorem of calculus says you take the integrand, and here's the integrand, p of something comma y, and then you take the variable, which was x, and you put it in there. So for this line integral, we just get p of x comma y. So the partial of f with respect to x is p of x comma y. Now, by the exact same argument, if you do the exact same thing to calculate the integral, the derivative of f in the y direction, well, it's not quite the exact same thing. The path you have to use is slightly different. So the first part of your path will go almost to x comma y, but just below it, and then the second part of the path will go straight up. Since y is changing on this blue segment, using this you can calculate the partial derivative of f with respect to y, and when you do that, you get q of x comma y. And this means that the gradient of f is capital F. And that means f is conservative, and so we're done.